like to give you a little bit of notes that I think I can keep pretty brief. About two-dimensional motion. Now, we already know a bunch of stuff about displacement and position and velocity and acceleration. So as much as we can use what we already know to support what we're going to do or how things are different when we move up to 2 dimensions rather than 1, like we were doing in Chapter 2, well, if we can tether all this new knowledge to things that we already know, then that's good, right? So in 1 dimension, we, depending on what the direction was, often it was back and forth like this, so we thought of that as like an x-axis. So we had position that was just given by a number, x. Now really, if we think about this, that number really was a vector. It was just a one-dimensional vector, right? Because it could be positive, which is a direction, or negative, which is a direction. It's just that in 1 dimension there's only 2 possibilities. So a positive and a negative is enough. So really that was a vector. So I could put a little vector hat on that. Right? So it had magnitude, whatever the absolute value of this is, and then the direction was whether it was plus or minus. And then in 2 dimensions, my position is going to be, there's different letters that you see. Our book, I think it's probably most common for that to be given as R. Position vector. You could think of that as kind of like being an R for radius, because if you imagine your your axes here, your I direction and your J direction, that position vector is like pointing from the origin to your location, which is kind of like, if you swung that all around, it's like the radius of a circle. So there's your position there. How about velocity? Well, in 1 dimension, we have, when we just say velocity, we mean, well, let's do this first, sorry. Let's do average velocity first. Your average velocity is your change in position over change in time. Right, which is final minus initial. How about in 2 dimensions? It's exactly the same thing. It's delta R, or delta T. And I would just like to point out to you the difference, although these look identical, just I wrote an X here and an R here. This is a 2-dimensional vector, so when you do this minus this, well, all the vector practice that we did, those problems from Chapter 3, you just get these in component form and you do the subtraction, right? It's just a little vector problem. And then you divide each one by that time, and then you would have the velocity in component form. Do you need to have the magnitude and direction of it? Well, you know how to do that, right? So all of those vector operations come into play here for finding that. And maybe I'll do an example of that for you in a minute. If you want the, if somebody just says velocity and they don't say average velocity, you would have to assume that they meant instantaneous velocity. I'm going to clarify that here. But if it just says, if you run into some situation and it only says velocity and you're scratching your head, does that mean average or instantaneous? It doesn't mean average velocity unless it says average velocity. This is the default. And that is dx dt. Now, we never wrote this with a vector hat on it, but it doesn't change anything about how we do how we do the calculus. Here, well, how does the calculus work here? It's the same if you have a vector, a position function, and you actually want to take the derivative of it. If you have it in its component form, which is typically the way you're going to see it, where there's like some function of t, I, and then some function of t in the j direction, you just take the derivative of each piece separately, and then that gives you a velocity function in component form. I will show you an example of that also. The average acceleration, well, here in one dimension, that was just change in velocity over change in time, right? Because average is actual change in, right? You need 2 points. It's like finding slope. And we could put a little vector hat on this. Of course, in one dimension, it's just positive or negative, but that still qualifies as being a vector, just one-dimensional. And here, how about my average acceleration? It's exactly the same thing. Just going to be two-dimensional vectors that I have to do this with. Right? Do you need the magnitude and direction of this average acceleration? Well, sure. You know how to do that, right? It's just vectors, easy vector stuff. And let's see. What else do I need to tell you? I don't really think that there's a whole lot else that I need to tell you. Oh, yeah, I do need to tell you a couple more things. Let's see. Total distance traveled. So total distance traveled is just, it's a very intuitive thing. I mean, it's the total distance that you've traveled. You just have to add the magnitudes of all, can I say the legs of your journey? I don't think we're always going to think of these things as journeys, but when you're adding several different displacements together, like do this, then do this, then do this, if you want the total distance traveled, you have to add the magnitudes of all of them. Whereas your total displacement is just the magnitude of the vector sum. So here you have to pay attention to what each magnitude is and ignore the directions. And let's see, if you wanted to find what is your average speed, not your average velocity, then that is total distance divided by your time, which is exactly what it was in one dimension. It's just that to find total distance, you have to add all these magnitudes, which is really what we did here. It was just easier in one dimension, and then average speed, total distance over time. Okay, so let me run through one example. And that should be enough. So I'm just going to make up a position function, and then we're going to find a bunch of things. This will probably have, I don't know, a whole bunch of parts. So given some position, sometimes this is written like position as a function of time, just like we would have f of x, and sometimes it's just given as r without the little parentheses t, which would be more like y equals, if you want to think about how this is connected to math things that you know. And let's see, let's say that the position is defined by this t squared plus 2. So that's the little function that defines what's going on in the I direction. And then this is what's going on in the j direction. And let's say that is in meters. Okay? And time is in seconds. So what are the things that we can do with something like this? So find the velocity function. We could do that. Well, the velocity function, velocity is the derivative of position. So I just look at this and say, what's the derivative of this? It's 2t. And then how about this? It's just 5. And that would be in meters per second. Ooh, that was easy. So what else can we do? How about if we find the acceleration vector as a function of time? Here it would be 2i, and then this, the derivative of 5 is 0, so it's just this constant 2i meters per second squared. So this is a situation where we have constant acceleration. Can you have variable acceleration? Sure, absolutely. You could have t's in there. Let's see, what else can we do? Find displacement from, if you're finding delta something, you have to have 2 times, right? From time 0 to time 3 seconds. Okay, so I need to find the position at those two. So since this is the final, I'm going to go ahead and do that first, because I know I'm going to be subtracting final position minus initial position to find this. So the position at time 3 is, well, I just need to plug that in, right? So 3 squared is 9 plus 2, that's 11i. And then 15 minus 3 plus 12j in meters. And then the position at time 0 is 2i minus 3j. So you want to know what delta r is. That's what that means. So that's 11 minus 2 and 12 minus negative 3. So that's the displacement. What if you needed to know the magnitude and the direction of the displacement? Well, you know how to do that, right? That's, you Pythagorize those. Just do that real quick. Oops, wrote that in the wrong place. Sorry. And the direction is the tangent inverse of 15 over 9, 59 degrees. All right. Let's see. How about if we do the let's compare the instantaneous velocity at time 3, which is very easy to find now that we have our velocity function. It's just 6i plus 5j meters per second. And if you wanted to find the magnitude and direction, you could do that easily here. How about if we wanted to compare that to the average velocity from time 0 to time 3. How do you do that? Well, average velocity is like finding slope. Average velocity is the difference in position, delta position over delta time, right? Change in meters over change in seconds. But you actually have to have the two of them. Now, I already did this here, right? So I don't have to do that again for these two. If it was 2 different times, well, we could do it again. But I have it here. So what is my delta R? It's this, 9I plus 15J, that's an I there, hat, meters, over, and then delta time is 3 seconds. So that's kind of an awkward way to put that, but when you're dividing, just like calculus class, when we see problems like this, or algebra since forever, you're dividing by one thing, and you have the 2 up here, so you can just divide each one of those. That's 3I plus 5J meters per second. That is the average velocity in component form, right? And then you can see this was the instantaneous velocity in component form. So what if I wanted the magnitude and direction? Let's do that real quick. So the magnitude of the average velocity, which is, by the way, the average speed. Here, no, that's not true. Sorry, scratch that. That would be true here. The magnitude of the instantaneous velocity, which would be the instantaneous speed, would be the magnitude of this. I'll explain why it's not the same here in just a second. So here the direction is tangent inverse rise over run. That's 59 degrees. And I want to point out that you could also, since we knew the magnitude and the direction of the displacement, that when you could have got these answers by doing the same thing. Do you know what you get if you take this, the magnitude of the displacement, 17.5, and divide it by 3? You get 5.8 meters per second. You know what happens to the direction? Well, the direction doesn't change. If this here, if you take a vector and divide it by something that's not a vector, the direction is not going to change. If you take a vector and divide by a vector, that is not a defined mathematical operation. That's not a thing. There are a couple ways of doing something that's like multiplication with vectors, but we're not doing any of that right now. So just a quick word about why you can't say that 5.8 meters per second is the average speed. That's because this thing is following a curved path, and to do the total distance, traveled, we would have to know how to find the length of a curve, and that is something that we will learn this year in calculus. And we will use that. We'll loop back around and think about how to do that with vectors in a motion context, two-dimensional motion like this. But we don't know how to do that yet. That's coming. It's pretty far down the road in calculus. So never mind what I said there. Just don't know how to do that yet. We can do average speed if we have like nice straight legs of the journeys. So then that's a possibility if we know the magnitude of each part of the displacement. All right, is there anything else that I need to, let's see, let's just also do, let's find the instantaneous acceleration at time 3. Well, the acceleration's constant, so it's always that. And then last thing, how about if we find the average acceleration from time 0 to time 3? Well, average acceleration, average anything, is like finding a slope, so that is delta v or delta t. So it'd have to have the velocity at time 3 minus the velocity at time 0 over 3 seconds. And I think I have those, don't I? Let's see. Well, I have one, so that's and then what's the velocity at time 0? Well, I have my velocity function here. So the velocity at time 0 is 0I plus 5j. You could have left that out if you want to. It's a 0. And let's see, the 6 minus 0 is 6I. 5 minus 5, that's 0. So it looks like it's all, and this is, oh, I should be including units up here. This is all meters per second, right, because these are velocities. So 6 divided by 3, that's all in the I direction. So it looks like I have 6 divided by 3 is 2 most of the time. And that's I, no j, meters per second squared. Now that's interesting. You might be looking at this and saying, wait a minute, 2I meters per second squared, that's the same as this. Well, it makes sense that the average acceleration is the same as the instantaneous acceleration here, because the acceleration is constant. So your average is going to be exactly the same as the instantaneous. So that all worked out. All right, that should put you in good shape for doing some problems at the beginning of Chapter 4.